Hi everyone, this is going to be the seventh and the penultimate weekly live session for the NPTEL course of River Engineering. This course is brought to you by the Swayam initiative and the NPTEL scheme. And this course is being tutored by Professor Subhashish Datta, who is a professor in the Department of Civil Engineering at IIT Guwahati, and I am the TA for this course, Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research in IISc Bangalore. So far all the videos have been uploaded almost immediately after the end of the weekly live sessions on this YouTube channel, and someone is there probably. And the files related to this course have been already uploaded on the Google Drive folder, so make sure to follow them up right after the class ends. So today is going to be the penultimate lecture, weekly live session for this course, and I thought of just choosing uh, one topic related to the eight weekly live eight 8 weeks content, that is about the meandering of rivers. Then we will wrap it up with a question about the Lacey's regime theory, and then we will go back to some of the previous questions. So my plan is to just discuss a few questions and formulations about the uh, lectures provided in the 8 week of this NPTEL course, and end up this weekly live session with some other prominent questions which came up in the earlier parts of our weekly live sessions. And as informed by you, I would be wrapping up this weekly live session in our next and eight weekly live session with a few of the important concepts and formulae which were discussed over the course of this entire river engineering course. So yeah, so we will start with the theory of meandering rivers. So rivers meander. We know that a lot. So due to that, they also change their positions pretty frequently. It is very common in alluvial rivers. That is the rivers prominently found in the northern plains of our country, like the Ganges, the Yamuna, Kosi. So these rivers happen to be huge trouble for human beings also, and cause devastation in the form of loss of lives or properties and many other such events. So first of all, river engineering, river meandering. It is nothing but the alternate meandering routes of rivers. So they keep on changing their positions until they form something known as an oxbow lake, and then this process again starts. This I also explained in the weekly live session zero. I mean the one which was a prerequisite for this course. So more detailed explanation about the meandering is given in that YouTube lecture video also. Yeah. So let us see how a meandering river would look like. So this is a meandering river. This lambda, the small lambda, is something which we call as the deflection angle. So this is nothing but the change in the. I mean, we already know that uh, theta in radians is a ratio of the arc length to the radius subtended by the arc. So this is the concept we are using here. So theta delta L in our case is the angle subtended. Angle subtended. So it is nothing but the ratio of the arc length to the radius, and it is supposed to be directly proportional to the tangent of the deflection angle. So this is one of the assumptions while we derive all the important formulations about the real river meandering cases. So this is one small scale zoomed in photo of the meandering scenario. Let us take another photo. The arc length in this case is delta x. The radius is r1 here. The radius may change because the focus point may change in meandering rivers. So the radius may be r2 in this case. Now what we're doing is that we are, yeah. So there are two different arc lengths also based on radius r1 and r2. So for this one, it may be delta L1, and for L2 corresponding to that, it may be delta L2. So the angle subtended between the two would be known as the gradient. So this we can also write as delta L2, which is the larger side, minus delta L1 by the total arc subtended, arc length of the chord. And if we suppose that the chord size is very small, then we can simply assume that the uh, that this direction is also this length is also basically delta x. So using this assumption, we can assume that the delta theta expression happens to be delta L2 minus delta L1 by delta x. So let us suppose this is the meandering scenario at time t dash, which is t plus small delta t, and this is at time t itself. Now we yeah, we will go to the next slide, otherwise it is very cramped. Yeah. Now we are just using the fundamental equation of chord and arc length. So delta theta, the angle subtended by delta x, is also equal to the minus 1 times the radius of curvature extended by it. So you might be wondering why this minus curve actually came into picture. This minus term is because as delta x is positive, delta theta will be negative, or vice versa, and that is why we have to put a minus sign in front of the r, I mean, in front of the right hand side of the equation to make the total equation positive. So we get delta x is equal to minus r delta theta, and delta L we already know is minus a delta theta by delta x. So let us suppose we want to know what is the change with respect to position of delta theta. I am denoting it as delta theta dash. So it would look like minus a. A is the arc length subtended here by delta x times the gradient, and the gradient would be in our case minus delta theta 2 by delta x plus delta theta 1 by delta x. So these delta theta 1 and delta theta 2 are the angles made by the horizontal at these two directions. So this is delta theta 1 and this is theta 2, delta theta 2. So let's move into this. I actually intend to start from the derivation so that we can finally get into a very good expression about the uh, meandering ratios, the sinusoidal nature, tortuosity, and everything else. So we are slowly coming up into that. If we take again the derivative with respect to position, we will get this would be the first derivative term, and this with this, I mean, again taking a derivative of it will produce the second order derivative delta theta 2 by delta x square. Okay. So first of all, we had some assumptions regarding this. These assumptions actually come from experiments which were conducted around 1960s on river meanderings. To be precise, 1966. So they assumed that the rate of lateral migration in rivers would be in meandering rivers would be proportional to the secondary flows, that is the mean annual river migration. So mean annual river migration can be represented as A by R, which I explained already. It is supposed to be directly proportional to the deflection angle, the tangent of the deflection angle, and it is supposed to be nearly equal to 11 h by r according to some empirical formulations. This thing is not important for our further discussion anyways. So let's move into the derivation. So we know that delta x is r theta 2 minus theta 1 or r delta theta. So it is minus r delta theta. Delta x is minus r delta theta. Again, you might be thinking why this minus term is arising. It's because if delta x is positive, then delta theta will be negative. So in order to make both the sides of the equation as positive, we are putting a negative sign in front of the right hand side. So we know this first thing, and we also know that delta L equal to minus a delta theta by delta x. So two of these things we have already discussed. Now channel position at time t dash, which is a very small, infinitesimally small change from t, that is delta. The infinitesimally small time width is basically delta t in our case. So we are more interested about the orientation angle, which is theta in our case. So the rate of change of orientation angle is, let us suppose we denote it as theta dot. So theta dot will be, it is a rate of change, so it is basically time derivative. So we are taking a very small increment in the time dimension, and this is denoted as this. It is nothing but the first derivative of delta theta, and we are writing it in terms of limits. So now moving into it, theta dash can also be written as limit delta theta tends to 0 minus a by delta x from our earlier expressions, which we discussed in the previous slides, this one, times, since it is delta theta dash by delta theta dash by delta theta x again, so it is delta theta 2 by delta x minus delta theta 1 by delta x. So this would be basically nothing but the second order derivative minus a del 2 theta by del x square. Now let us suppose we choose the orientation angle as a sinusoidal function. Uh, Let us say the orientation angle is a sinusoidal function where x is the what do we say, the distance along the path of the river, and theta dash, sorry, theta dot was what we found as minus a del 2 theta by del x square. So one thing we are seeing is that if we take a sinusoidal term, a representation for theta, or a cosine representation of theta, we will get a self-preserving nature. What is or self-generating nature? So what do I mean by that? If you take the first derivative of this, you will get delta theta by delta x is equal to cos kx. Let us suppose you take another derivative of this, so you will get minus k square sin kx. Minus k can be written as minus a again sin kx. So it is nothing, I mean, we are again getting back into the term which we already explained. So this is why it's known as the self generating form. I'm just explaining. I mean, my motto here is to explain why we almost always represent the meandering formulations using either a sinusoidal or a cosine function. This is what I wanted to explain, because they basically get self-generated again because of the double derivative form. Now let us just look at the sine generated curves. I mean the sinusoidal curves. Let us suppose the orientation angle of river is theta, as we were already doing earlier, and the downstream distance equal to x. Now, through their several experiments conducted, Langevin and Leopold, these two researchers in 1966, gave a formulation that the orientation angle can be written as theta m cos 2 pi x by L, where theta m equal to the maximum angle at the origin and L is the sinuous river length. I mean the curved one. So let us take the R as the radius of curvature as we have been already using in notation. So according to the fundamentals of arc length and radius, we know that 1 by R is equal to minus d theta by dx. This equation is actually universal and it's followed everywhere for any kind of arc and subtended arc length and subtended arc formulation. We move forward into this formulation again. So d theta by dx from equation number 1 would look like minus d by dx theta m sine 2 pi x by L. Okay, so we just basically substituted theta with theta m cos uh, 2 pi x by L. Okay, so let us look at it. 1 by R, because d theta by dx is equal to 1 by R, so it will finally become 2 pi by L theta m sine, it is cos, sorry, 2 pi x by L. So this is the final formulation for the radius of curvature for this. Now let us take several cases. I mean, how the meandering happens. So far, I have already explained how what are the basic meandering equations and formulae. Let us now check several what do we say cases for the subtended angle, orientation angle, and see how they vary. Let's see that now in the next slide. A very similar question is asked in assignment number 8 also, by the way. Okay, so let us suppose we firstly take a case where there is no meandering at all. This is the river. The river flows from the top of the slide to the bottom of the slide. Let us say lambda inner case is the river length. So for this case, the subtended maximum angle would be 0 degree. It's pretty easy to visualize. The sinuosity, which is nothing but the curved length to the straight length traversed by the river. In our case would be 1 because they both are same. There is no curve at all. Wm by lambda, which is basically a case of no meander. So Wm is basically the meandering width. So since it is 0, so for this case it is 0. Then lambda by r min. In this case, the radius of curvature will tend to infinity. So lambda by r min would basically be 0 because it's a straight reach of river. Let us take another case. But in this case, there is some sort of meandering in the river. The river again flows from the top of the slide to the bottom of the slide. Okay, so this is the maximum angle subtended. In our case, let us suppose it's 30 degree. So theta m for this case will be 30 degree. The sinusity would be 1.07. I'm just giving you a few numbers. We will again discuss how the numbers actually came into account. Wm by theta lambda for our case would be 0.17, and lambda by r min for this case would be 3.1. We can again vary the maximum subtended angle to, let us suppose, 90 degree. So it would be 2.12 the sinusity, 0.80 will be the Wm by lambda ratio, and 4.6 would be the lambda by r min ratio. And for 120 degree, the numbers would be 5.9, 2.3, and 2.2. Okay, so let us see one thing first of all. What do we see? The sinusity is never less than 1. So this is pretty obvious also, right? The curved length will always be greater than or at least equal to that of the straight line length. So it would be equal to the straight line length in case where there is no arc angle at all, no subtended angle at all. I mean, the subtended angle is 0, or the river reach is entirely straight. So that is why we are observing that the L by lambda ratio in all the cases happens to be greater than or equal to 1. And it is equal to 1 in the case where the river reach is entirely straight. Okay, now we will discuss some of the most important terms associated with the meandering of rivers. Okay, the minimum radius of curvature Rm is represented as Rm is equal to the length traversed by 2 pi theta m. Theta m is the maximum angle subtended here. Then there is another term known as the meander length, which we represented as capital gamma, 0 to L. The subtended length is 0 to L. Cos theta dx here. Why cos theta? So this is cos theta because this term is what we are finding. So this is the projection here. So we just put the value of theta. So we will get cos theta m cos 2 pi x by L dx. Now one thing we are observing is that solving this integral is not easy at all. So this integral is represented in the terms of the length traverse by j naught times theta m. And j naught is something known as the Bessel function mathematically, because solving it is not easy. Bessel function actually needs quite a lot of complex calculations. So this j naught theta m is equal to the zero order Bessel function of the first kind. This is just mathematically, because solving this is not so easy. It is not an explicit integral basically. This Bessel function can be basically what do we say, approximated as 1 minus 0.25 theta m square plus 1 by 64 theta m power 4 minus 1 by 2304 theta m power 6 plus it goes on till infinity, and theta m happens to be in radians in this expression. So as we move into the higher order terms of theta m, they will basically tend to diminish. Then we are concerned about the meander width also. Meander width, which we represented as Wm, would be 2 times 0 to L by 4 sine theta dx. Sine theta, why? Because it's a projection in the perpendicular direction. This projection is what we are concerned about here. And why L by 4? This is also very important. Why L by 4? Because for one oscillation of the sinusoidal or the cosine wave, there is a symmetry after L by 4 intervals, position intervals. So that is why it is just till L by 4. So we are basically utilizing the I mean we are exploiting the evenness of the sinusoidal function. Okay. because sine function happens to be even, so it was actually supposed to be integral was actually the limits of the integral was actually supposed to be from 0 to L by 2, and since it's even centered around L by 4 intervals, so we can say that it is equal to 0 to L by 4 sine theta dx. Okay, so let us just put the expression values. So it would be simplified as theta m cos 2 pi x by L dx. I'm just putting the value for theta. Again, solving this expression is not easy. So we are again putting in a similar expression as the Bessel function. It would be L by 2 h naught theta m, where h naught is the Struve function. Let's look at the next slide. H naught theta m. H naught is the Struve function, and it is represented as 2 by pi theta m minus theta m whole cube by 3 plus theta m 5 by 15 square minus theta m 7 by 105 square, and so on. And theta m, I mean, it need not be told that theta m is in radians and not degrees. Now let us look at some of the important dimensionless parameters regarding meandering rivers. Number one is the sinuosity, represented as capital omega L by capital gamma, which is nothing but the river length. I mean the curved length by the straight length. It is represented as 1 by j naught theta m. I mean Bessel function of the zeroth order, but of the first kind. Then the relative meandering width is equal to the meander width by the straight length, and it is represented as h naught theta m by 2 j naught theta m. Then relative minimum radius of curvature is delta by rm 2 pi. These are by definitions, by the way. Or this can also be written as 2 pi theta m j naught theta m. Okay, so we are done with the metering part. I believe it was very boring, but I needed to explain this for one of the questions of your assignment. So that question is relatively very easy actually. You just need to use this expression to solve that assignment 8 problem. So that you should be done with. Okay, so let's solve another sort of question which is prominently asked in the assignment number 8. The question asks that according to Lacey's regime theory, what will be the regime scout depth for a channel in soil having silt factor of unity and carrying a discharge of 96 meter cube per second? The base width of the channel is 12 meters. So Lacey's regime theory is valid only for alluvial channels, alluvial rivers. It is not valid for most of the peninsular rivers basically, because they have a hard rock aquifer system and not an alluvial river system. Okay, So there are a few equations related to them. So the regime width will be equal to 4.75 square root of q. Normal scow depth according to the Lacey's theory will be represented as, let us say, r, and it is 0.473 q by f to the power 1 by 3. This equation will be applicable only when the river width is equal to the regime width of 4.75 square root of q, and not everywhere else. For any other value of, I will write it down, applicability for case when river width equal to regime width, or else it is not. For any other value of actual river width, we use another expression given by Lacey for the normal scow depth, which is 1.35 q square by f to the power 1 by 3, where q is equal to capital Q by b, discharge per unit width. So the small q is discharge per unit width, and f is the silt factor, b is the base width of channel. Okay, so the question wants us to find out the scow depth. So we know that it is 1.35 is q square by f to the power 1 by 3. We have been given capital Q, we have been given b. So we can find out small q from it. So it is 1.35 q square, small q square, f by 1 by 3. So it is 1.35. So it is q by b. Q was 96 meter cube per meters per second, and b is 12 meters. And the silt factor is given as unity in the question, so it is like this. It will come out to be 5.4 meter, the scow depth. Okay, so this ends the question, but I will give another a few more equations, just because these equations are very necessary for this course. So there are a list of equations according to the Lacey's theory. Number one, the hydraulic mean depth is represented as r. Let us say r is 5 by 2 v square by f, where the symbols mean what we have defined in the earlier slides. Number second, area of channel section. It is by the fundamental laws and not by Lacey's formulation. It's nothing but the discharge by the flow velocity. Then the wetted perimeter is 4.75 square root of q. Then the regime mean velocity is qf square by 140 power 1 by 6. And number 5, the bed slope. One of the question actually wants you to calculate the bed slope also in assignment number 8. So that would be f to the power of 5 by 3 by 3340 q to the power 4 by 6. So these expressions plus the one for the scow depth will constitute and everything about the Lacey's theory relevant to this course of river engineering. Let's move into the second question. Okay. A rectangular channel carries a certain flow for which the alternate depths are found to be 3 meter and 1 meter. The critical, yeah. So by now we have already finished what I wanted to discuss for relevant to lectures, uh, lecture number 8. Okay. So now we move into the previous lectures, which and the remaining questions which I will be discussing here would be relevant to your final examination of this course. So these are relevant to the previous lectures. So the first such question is, a rectangular channel carries a certain flow for which the alternate depths are found to be 3 meter and 1 meter. The critical depth in meter for this flow is, okay. So what exactly are alternate depths? The alternate depths are the depths for which the specific energies are equal. This may be even asked in the final exam. So the alternate depths, let us suppose the specific energies are equal for them. So for section 1, the alternate, the specific energy will be y1 plus v1 square by 2g. For section 2, it would be y2 plus v2 square by 2g. So this will give us y1 plus q square 2g y1, because V is basically Q by A and A is basically by, and if we substitute capital Q as equal to sorry capital Q by B is equal to small q, we will get this term finally. I mean, for more reference about it, please go back to some of my previous weekly live sessions. Y2 plus Q square by 2G Y2. So here, one of the alternate depth is 3 meter, the other is 1 meter. So let us just put the expressions now. 3 plus q square by 2g into 9 equal to 1 plus q square by 2g, sorry, this would also be square, into 1. So solving it, will get q to be 6.65 meter cube per second per meter, the discharge per unit. However, the question actually wants us to calculate the critical depth. So we know a very nice expression between the critical depth for a rectangular channel and small q. We'll be utilizing it in the next slide. The critical depth for rectangular section is q square by g to the power 1 by 3. We already explained it in our earlier sessions. So it would be 6.65 square by 9.81 meter per second square power 1 by 3, which comes out to be 1.65 meter of the YC. Let's move into the next question now. In a triangular channel, the critical depth is 2 meter. What is the corresponding least possible specific energy? Okay, we just use the expressions which we derived in our previous sessions. 1.25 times yc is equal to the critical or the least specific energy. So just put the expressions. 1.25 into the critical depth is 2 meter. We get 2.5 meter as the specific energy. So some of the expressions I believe that you need to remember for your exam. So the expressions relevant to the critical depth for a triangle, for a rectangular channel, for a triangular channel, those ones you need to remember. And for trapezoidal or maybe circular cross section, it would be better if you memorize the generalized expression which we discussed earlier. Okay, moving into the fourth question. If the Froude number of flow in a rectangular channel in a depth of flow y naught is f naught, then find the value of yc by y naught. Okay, so Froude number is given as for y naught. The Froude number is given as g naught f naught. So this is the expression for Froude number. and it is a rectangular channel, so we can straight away write that A by T is basically nothing but y, the depth of the flow. So just squaring this term, we get v square by g y naught. Rearranging it after getting our substitutions, we convert v into small q, that is the discharge per unit width. This implies from this expression y naught cube equal to q square by g f naught square. So this is the thing for y naught. We need to find out another similar expression for yc, which is a critical depth, and that would come out from uh, the Froude number for critical flow, which is unity. Let's find it out in the next slide. So for a critical flow, the velocity will be critical velocity, and the depth will be the critical depth, and the Froude number is definitely equal to 1. So from the similar expression which we derived earlier, we will get QCQ equal to GYCQ. Finally, just by dividing the two expression, YC by Y naught cube equal to F naught square, this implies Yc by Y naught equal to F naught to the power 2 by 3 is the final expression. Let's move into the next one. If y1 and y2 are the alternate depths of a rectangular open channel, then derive the expressions for the critical depth and the specific energy. Okay, y1 and y2 are the alternate depths. So alternate depths are the ones in which the specific energies are constant or the same. So specific energy is constant, or specific energy relevant to depth 1 is y1 is equal to the one related to depth 2 y2. Y1 plus V1 square by 2g equal to Y2 plus V2 square by 2g. This is just the Bernoulli equation excluding the datum term, because the datum here happens to be at the river bed itself. Y1 plus Q square by 2g By square b by 1 square, because v is equal to q by a, so a here happens to be b times y. We just substituting y with y1 because we are concerned about section 1 is equal to y2 plus q square. The discharges are definitely same, 2g according to the continuity equation, y2 square. Okay, so this is the thing. Now we convert this capital Q into small q again. So Q by B, capital Q by B is small q. So capital Q square by capital B square will be small q square. That is what we are doing in the next expression. Y1 plus Q square by 2g Y1 square equal to Y2 plus 2g Y2 square. This is what we have derived so far. Now we know that for rectangular channel, because the question asks you to solve for rectangular channel only. For rectangular channel, ycq equal to q square by g. This is a critical depth formulation as a function of the discharge per unit width. So we just put this in an expression, y1 plus ycq. Just substitute small yc for small q. 2y1 square equal to y2 plus yc cube by 2 y2 square. Taking yc cube by 2 common, 1 by y1 square minus 1 by y2 square equal to y2 minus y1. So from it we get the critical depth expression finally as 2y1 square y2 square by y1 plus y2 whole power 1 by 3 as a critical depth. We also need to find out the specific energy for it. So let's do it. Specific energy equal to E equal to E1 equal to E2, because y1 and y2 are alternate depths. E is equal to y1 plus yc cube by 2y1 square. We are just using the same expression again, but for one section 1 only. So this means that E equal to y1 plus 2 y1 square y2 square, which is substituting the expression which we found earlier. 2y1 square y1 plus y2. E is equal to y1 times y1 plus y2 plus y2 square by y1 plus y2. So finally we get the so, so finally the specific energy will be y1 square plus y2 square plus y1 y2 by y1 plus y2. So this is the final derivation for the specific energy when we know the two alternate depths already. Let's solve one last question for this weekly live session to wrap it up. But this question has been asked quite a lot of times, and there is every possibility that such questions can be asked in the final exam also. So that is why we thought of discussing it. For an unsteady open channel flow, the area average flow velocity is given as u is equal to 10x square and flow depth as 5x square t square. The top width can be taken as 3x square and area of flow as a is equal to 25x square. Then find out the lateral flow at x equal to 1 meter and t equal to 5 seconds. Okay. So we again go back to the Saint Venant's equation. For an unsteady open channel flow with lateral flow, the Saint Venant expression looked like this: u delta h by del x plus hd del u by del x plus del h by del t, where h is the depth of the flow, by ql by t. Ql is a lateral flow, and capital T happens to be the top width, and hd here is nothing but a by t, hydraulic mean depth. So we need to find it out first. A is given as 25x square. 25x square. T is the T given. Yeah, top width can be taken as 3x cube. So it is 3x cube. So it is basically 25 by 3x. That is the hydraulic mean depth. Now let us solve each of the expressions. Number one is del h by del x. So it is del by del x of h, and h is what? Flow depth. Flow depth is 5x square t square. Okay, so we just need to take the partial derivative with respect to position, so it will come out as 10x t square. The second term in the expression is del u by del x. So We need to find it out. What del u by del x is. So it is del by del x of something. Is the u given? Yeah, u is given as 10x square. 10x square. So take the partial derivative, we get 20x. The third term is a time derivative term, del h by del t. So del h by del t is basically del by del t of h. H was given as, the flow depth was given as 5x square t square. So it will be 5 times 2, 10 x square t. So we just need to substitute all the terms in the original Saint-Venant's expression containing lateral flow. Okay, so the original expression was u del h by del x plus hd del u by del x plus del h by del t equal to ql by t. I have to take another slide for it. So 10x square times 10x t square plus the hydraulic mean depth was 25 by 3x, which is what we found out, times 20x plus 10x square t is equal to ql, the lateral flow, by 3x cube. This implies it is 100x cube times t square plus this would be 166.67. X terms will get cancelled, plus 10x square t equal to ql by 3x cube. We need ql for this solution, and that is to be taken at, uh, we have been provided something, right? Yeah, at x equal to 1 meter and t equal to 5 seconds. So this would be 100 1 cube 5 square plus 166.67 plus 10 1 square 5 equal to ql by 3 1 cube. So the ql will be finally found out as 8150 meter cube per second. This is a very probable question actually. I mean, Saint-Venant equation is something, uh, is basically the crux of this course. So such questions may be very possibly asked in the examination. So let me just go through what we discussed today. We firstly discussed about the theory of meandering rivers. They happen because of series of aggradation, deposition of the sediment particles in the alluvial rivers. A more detailed analysis or discussion on it is given in the assignment number zero's YouTube video. Yeah, so these were just the derivations, but from it we found a very important term. Yeah, this one for the orientation angle. Then we found out the sinuosity for different orientation angles. We observed that as the orientation angle increases, the sinuosity also increases, which is pretty obvious, right? I mean, as it is increasing, uh, the curved length is also increasing. Then we found out the meander length, and we found that the integral is actually pretty hard to solve. So I mean, we have expressed it in a form of the Bessel function of the first zeroth order Bessel function of the first kind. Similarly, the meander width also contains an integral which is very hard to find, and it is something known which contains the Struer function. So these are actually pretty big polynomial expressions. Then we observed three different prominent dimensionless parameters concerning the meandering rivers, the sinuosity, the relative meander width, and the relative minimum radius of curvature. Then we solved a question about the Lacey's regime theory. Uh, I thought of again giving a list of the Lacey's theory formula, the most important ones. Then we solved a question about the alternate depths, because these questions will be very prominently carried out. I mean, prominently covered in the exams also. Then one about the triangular channel. Similar, very nice expression is given for the rectangular channel also. It's basically 3 by 2 times yc for EC. And for the other kinds of open channel section, please go through the generalized expression which we actually discussed. Then we discussed two derivation based problems, and we wrapped up our today's discussion with a question based on the unsteady state open channel flow, that is the with lateral flow consideration, which is the continuity expression counterpart of the continuity expression for the Saint-Laurent's equations. This is what we discussed today. Uh, the next class I will be only discussing the probable important formulae, and we will be solving a set of the most important questions, which I believe may be important for the examination. Any doubt, anything to ask?
So,
Yes, please.
so for the exams, whether the derivations will be asked like
No. The
expressions and
derivations will not be asked, but I thought of just going through them, because otherwise, if I just introduce the equation straight away, then it becomes very
uh,
boring. I mean, that is what I felt as a student earlier on. So I
okay. Will
thought
it be
of,
multiple choice questions or
yeah,
it's a
please ask.
computer based exam?
Yeah, please
Is it?
ask, please ask.
It's a computer based exam, no, sir. This
Yes,
one.
yes.
So it will be multiple choice question type or descriptive type questions.
No, there will be no descriptive type question. They will be all multiple choice and or numerical type. I mean, you have to put a number,
Yeah.
right? The
Okay.
questions will
Okay.
be very similar to the kinds of questions asked in the assignments. So if you, before the next class, I would just recommend that you go through the assignments very well, so that we can have a
Okay.
very healthy discussion. Okay. So
Yeah, so one more thing, sir. Actually, for the solutions for the assignments 1, 2, and 3 has been released,
okay,
and but for me that link is not working. It's not going to that site.
okay.
Anyone else has given this problem, has mentioned about this problem?
Okay, actually, I have also enrolled for this course. I was asked to enroll for this course as a TA. Okay, and I am also able to not able to find out the assignment. Download the
Solutions.
assignment. So probably it is because I have not paid for the course. I am of course not a student of this course. I enrolled just because I am a TA. So have you paid for this course?
Yeah, I have paid for this
Then you
course
should
also.
contact immediately, put a mail in the discussion forum, okay. And you got a reply from the NOC mail, right?
Yeah, yeah,
Yeah, he
I
is
got it.
actually
Yeah,
Mr. Mridhupavan Deka. He's the TA from IIT Guwahati. He's the person who actually reply. He was replying from the NPTEL course email. So he will be doing the same. I mean, he will be helping you out in this, in that case, because I don't actually deal with the assignment related things. My work is only, having one weekly live session. That's it. Okay, so for that there
understand.
is Mr. Deka, I mean from IIT Guwahati, who is a student of Professor Datta. I mean the original tutor of this course. You please put in a mail there in
Yeah.
the discussion forum. I will also make sure to convey it immediately after this class ends. I will WhatsApp him immediately. Okay. No need
Okay,
to
sir.
worry
So
about that.
in the assignment number one,
Yeah.
question number 9, actually, can you just show it in the next class?